All right, so today we begin to talk about hypothetical rules. We will introduce our first one, which is the rule of conditional introduction. And first we'll talk a little bit about the nature of hypothetical reasoning at an informal level. Okay, so the last two basic rules that we introduce are different than the first 8 that we've already learned, in that they introduce what amounts to different forms of proof. They're both called hypothetical rules because they involve reasoning on the basis of a hypothesis that is not actually used as a permanent premise. So in this context, what we mean by a hypothesis is that it's essentially a temporary assumption, We introduce it, or we suppose it, or we hypothesize it to achieve some particular goal. And then later, we discharge the hypothesis from the proof. So the important thing to understand is that you really already know how to do hypothetical reasoning of this kind. It's sort of built into the way that we reason in natural language. For example, if you're trying to decide whether to say, answer a text while driving, hopefully that's not a tough decision for you, you might ask yourself whether that's really a good idea and do a little reasoning. And the reasoning might go like this. Suppose I do answer a text while driving. Then my attention will be divided between texting and driving. If I'm not paying attention to driving, I may crash and even kill someone. The text is probably of very little importance, and there's little value in answering it immediately. But if I crash and kill someone, my life will be ruined. So maybe I better answer the text later. Now, we'll leave aside the question whether we could actually prove that deductively. The important thing to understand is that this is hypothetical reasoning, and the hypothesis in this reasoning is the initial statement. Suppose I do answer the text while driving. So rather than actually answer the text and just figure out what happens, experience what happens, what you do is you imagine or hypothesize doing it, and then you work through the logical consequences in your head. Essentially what you're doing is exploring a possible world. Now, hypothetical reasoning of this sort is really a remarkable ability that, as far as we know, only humans have. Maybe other aliens have it, but we haven't experienced any aliens yet. And insofar as it helps us to anticipate and control our futures, it's very much the basis of human intelligence and also human free will. All right, so let's introduce the idea of conditional introduction, our first hypothetical rule. So the rule of conditional introduction, which we write arrow I, is used when we need to derive a proposition whose main operator is a conditional, which is to say a proposition of the form if A, then B. So to begin to see why we need a rule like this, imagine that I were to ask you to prove this. If P, then Q. If Q, then R. If P, then R. Now you can probably see that this is perfectly valid. In fact, it's a famous logical rule called hypothetical syllogism, which we'll use eventually. And you can see that if one of our assumptions were P, we're not given P as an assumption, but if one of our assumptions were P, we'd be able to easily derive the conclusion R by just 2 applications of conditional elimination. Right? So if we had P, we'd be able to get Q by conditional elimination, and then if we had Q, we'd be able to get R by conditional elimination. But we're not being asked to derive, we're not given P, first of all, and we're not being asked to derive R. We're being asked to derive the conditional, if P, then R. So if you were to try to work through this informally, you'd probably say something like this. Well, just suppose we had P. Then we'd have Q by conditional elimination. But if we had Q, then we'd have R by conditional elimination. So clearly, if P, then R. And that's right. So basically, we need a rule that allows us to reason in this way. And that's what conditional introduction is. It's a rule that permits us to reason in a way that's quite clearly valid. Now, what we need to do is we just need to formalize the operation. And as it turns out, that's just a little bit more involved than our other rules. It's actually quite a bit more involved, but it's not that difficult to follow. Okay, so let me just show you a formalized version of this way of proving things without explaining too much, and then I'll go back and explain it in some detail. So here's the actual proof that we couldn't do. And here's how we actually do it. First, we write down our assumptions in the normal way. And then what we do is we suppose or hypothesize P. So you'll notice P has been indented, and that's very important. We hypothesize P by indenting it, and we write H because it's a hypothesis. Now, once we have done that, once we've hypothesized P, then what that means is that what we're trying to do is deduce R, right? So we hypothesize P because we recognize that this is a conditional, and we only do conditional introduction when we're trying to prove something that is a conditional. We hypothesize P and we try to derive R. So we already know we can do this. We have the tools for doing this. And notice we stay indented. We apply it. We get Q by 1,3 conditional elimination, and then R by 2,4 conditional elimination. And so now we have actually hypothesized P and we've gotten R. So effectively, we have shown that if P, then R, right? So how do we make this so that we can actually infer the conditional if P, then R? Well, we just have a little mechanism for doing that. And the mechanism allows us to write down, right at this point, if P, then R. And what we do in the justification is we cite the line where the hypothesis occurred, which is 3, and then we cite the line where we got the conclusion, right, that we wanted, which is R. So we now have if P, then R, and so we write if P, then R. Now, after writing if P, then R, because we derived R from P, and writing 3,5 conditional introduction, what we do is we drop a line like that. And that's a very, very important thing, because that line actually tells us that H, and in fact, everything we used to derive our conclusion is now discharged from the proof. The line tells us these were just there temporarily to develop some conditional. And now we're no longer able, if this proof, for example, were to go on further, this blue line would tell us that we are no longer allowed to use these propositions behind the blue line. It's essentially a little jail for those propositions. Okay, so that's our first complete conditional elimination proof. Now, I'm just going to now go back through this and give you some little text boxes to look at, but I'm just repeating what I just said. So the first step is we see that we need to derive a proposition whose main operator is a conditional. As we'll see later, it doesn't always have to be the main conclusion, but it has to be a conditional. And then we hypothesize the antecedent of the conditional, indenting it and labeling it with an H for hypothesis. So then we try to get whatever it is we need, which is always the consequent, right? And this is just using all of the rules that we know how to use. And here it only took 2 steps, but it may take 20 steps. Then that will just lengthen the conditional introduction part of this proof. But we attempt to derive the consequent, having hypothesized the antecedent. We attempt to derive the consequent, and here, of course, we have succeeded. And we keep it indented until we have succeeded. And then immediately after succeeding in doing that, we assert the conditional. And when we assert the conditional, we take away the indent. I didn't write that here, right? So remove the indent. And then the justification of writing this conditional is that we draw this straight line. That's part of the justification. And that we write the initial hypothesis and the derived consequent line numbers right here, followed by conditional introduction. So in performing step 5, what we've done is we've discharged the hypothesis from the proof and everything we use to derive the consequent. And once we do this, we're not permitted to go back inside here and use any of these for any future, for anything in the future. Now, there's nothing in the future of this one, but later we'll see that we might do conditional introductions for the purpose of getting other conclusions, other more basic conclusions. And then, very important to remember that no proof is complete if it contains an undischarged hypothesis. So once you take on a hypothesis in a proof, you are committed to at some time getting rid of it. If you don't get rid of it, then the proof cannot be finished. Okay, so that's the whole concept. I would suggest spending a little bit of time going back through what we've just said until you really feel like you understand it. But now we're going to move on to some interesting applications of this concept. Okay, so this is just a restatement of the process that I had written in the little yellow boxes on the previous slide. And this is mainly here just for the benefit of people who are looking at the slides, but you might take some time to review it. Before we show you some applications, I want to try to warn you about one of the most basic mistakes that people get involved in when using conditional introduction. It's very peculiar, but you will at some point find yourself tempted to do it at least. So by far the most common mistake in performing conditional introduction is attempting to apply it to a conditional that does not even need to be derived, typically because it's an assumption already. So for example, suppose you are asked to prove this. Now this is in fact a valid argument, but we don't actually have the ability to prove this yet. We need our second hypothetical rule, negation introduction, to do this. But suppose I was being an idiot and I gave this to you to prove, and you were flailing around for ways to do it, you might, out of desperation, try something like this. Well, this is fine. You have written down the two assumptions correctly. And then you hypothesize R. You say, maybe I can do this with conditional introduction. And why would you do that? Well, presumably what your eye is attracted to is this conditional right here. And you can see that if you have R, then you would have not P by conditional elimination, right? Which in a kind of confused way, you'd be thinking, and that's after all what I want. So suppose you hypothesize R, and then by conditional elimination, you get not P, which is perfectly legitimate as far as it goes. And then you say, oh, good. Now I've got if R, then not P. And all of these steps are actually correct. You do have if R, then not P. You hypothesized R, derive not P, so you can assert if R, then not P by 3 through 4 conditional introduction. But here's the problem. You weren't trying to prove if R, then not P. You were trying to prove not P. So you haven't accomplished what you need to accomplish. And then the silly thing is, and you'll feel silly when you do it, especially after I've told you, but you will still be tempted to at some point. It's virtually guaranteed. The silly thing is that you've just proved an assumption. Now, there's no reason to do that, of course. There's no reason to prove an assumption. An assumption is something you're just given to prove other things with. So that's the main temptation. And the way you avoid that is just to realize that the only time you use conditional introduction is if what you're trying to derive is itself a conditional. So here you were instructed, your task was to derive not P. Well, that's not a conditional. So you would not be using conditional introduction in any straightforward way, at least, to derive not P. So always remember that if you're trying to, if you're using conditional introduction, it's because what you are trying to demonstrate is a conditional. All right? So no formal error actually occurred here. It's just that we derived an assumption, which is completely pointless. And so just write this on your back of your hand. You never, ever prove your assumptions. Assumptions are givens that you use to prove other things with. All right. So let's do some important applications of conditional introduction. Wouldn't be a bad idea to take a break right about now, unless you're feeling really energetic. About halfway done. Okay, so proving conditionals that aren't your main conclusion. Often you'll use conditional introduction to prove a conditional that is not your main conclusion. For example, you might need to prove a conclusion whose main operator is a conjunction, like if P then Q and R. And in this case, you might choose to derive if P then Q, the first conjunct. You might choose to derive if P then Q, and then and by conditional introduction, and then get the whole conclusion through, say, an application of and introduction. So let's look at a proof where we use conditional introduction to derive a conclusion that's actually a conjunction of two conditionals. So we'll prove from these assumptions, we'll prove this conjunction. And so the basic thing we're going to do here is we're going to say, and this reasoning is quite familiar to you, you say, oh, this is a conjunction, so I bet I need to prove this, and then I need to prove this, and then I'll put them together. And that's exactly right. But now what you'll do is you will prove if P then Q using one application of conditional introduction, and then you'll prove if R then S using another, and then you will put these two together at the end of the proof. And it's actually a fairly straightforward process, right? So we take on our three assumptions, and then you say, first let me see if I can prove if P then Q. So by the method of conditional introduction, you'll hypothesize P, and then in the familiar way, you would get S through conditional elimination, and you would also get Q from conditional elimination. So 1, 4, and 2, 5 conditional elimination. And then you'll notice, of course, that you have, on the basis of your hypothesis P, you have derived Q. So at that point you say, aha, if P then Q. I've just demonstrated if P then Q. So you'll write that down and drop a line. So now P, S, and Q are all bracketed. They are removed from the proof. This line removes them from the proof, and so you can't go back in here and touch these anymore. But notice that if P then Q, which is not behind the line, is now perfectly available to you. So you can, if you get if R then S by a similar process, you'll be able to add that to P then Q with and introduction. So now you say, okay, now what I want is if R then S. So I'm going to hypothesize R, just like I hypothesized P. I am going to get P by 3 and 8, conditional elimination. And then I'm going to get S by 1 and 9, conditional elimination. And then I'll say, good, now I have actually gotten if R then S. So once again, I will assert that conditional, drop the line, and now all of these, this hypothesis and what I derived using the hypothesis are, again, off limits. But now you'll notice I have if R then S. So I have the two conditionals now free and clear that I need. And so all I have to do is put them together with one application of and introduction, 7, 11, and introduction. Okay, so that's a very straightforward example of how I would go about proving a conclusion that has multiple conditionals in it by doing multiple conditional introductions. Right, so I mentioned a while ago that the rule of disjunction elimination starts to become more interesting when we can actually construct the conditionals that we use in this. And the rule of conditional introduction is what we've been waiting for in order to do this. So remember that or elimination or disjunction elimination is a rule that depends on two conditionals. So we have A or B, if A then C, and if B then C. And if we have those conditionals, we can conclude C, as you know. So in the easy cases, the conditionals are just given to us in the proof. But in the more interesting cases, we actually need to construct the conditionals using conditional introduction. So this sort of raises the ante a little bit and puts us into a world that is exceedingly more rich in terms of what we can achieve. So let's do one of these. So we have four assumptions, P or Q, the disjunction, if P then S, if S then R, and if Q or R, Q or M then R, and we're being asked to derive R. Okay, so now we are doing conditional introduction, and you might just say, well, look, I mean, R is not a conditional, and you just told me that we don't use conditional introductions if we're not proving a conditional, and that's right. But we might want to prove a conditional that's not our conclusion. We might want to prove a conditional for the purpose of doing a or elimination. So if you look at what we have here, we have P or Q, and if we assume that P or Q is going to be critical in our proof, that it's not just there for no reason, then if we're going to use P or Q to derive R, we might have to show if P then R, and we might have to show if Q then R. The reason I say show is because if we look here, we can see that we're not given if P then R, and we're not given if Q then R. But we know that if we could construct if P then R, right? If we could construct if P then R, which we could just write down, construct if P then R, and construct if Q then R, then we could assert R for elimination, right? So let's see if we can do that. Well, how can we construct if P then R? How could we do that? Well, the way to do that is to hypothesize P. All right? And see now if we can get R. Because if we can get R, we can assert if P then R. So by hypothesizing P, now if you look at the premises, you can see that you can have S by 2,5 conditional elimination, and you can have subsequently R by 3,6 conditional elimination. So in fact, you have just demonstrated if P then R, right? So having demonstrated if P then R, you can write if P then R. Get rid of that. Okay. So you can write if P then R, and by 5 through 7 conditional introduction, and you drop your line, which of course, as you now know, makes all these things off limits, but you now have if P then R. Check. So now what you need to do is see if you can get if Q then R. Same process, hypothesize Q, and having hypothesized Q, you try to get R. Now this is a little bit different, but it's something you're already familiar with. Line 4 contains the assumption if Q or M then R, but you know how to get Q or M by adding it in with or introduction. So you now have Q or M by 9 or introduction, and now with 4 and 10 you have R by conditional elimination. So now you have demonstrated that if Q then R, and so you can write if Q then R and discharge that hypothesis. So now you have if P then R, and you have if Q then R, and you have your original disjunction, right? And so by 1, 8, and 12, you are permitted to assert R by or elimination, and you're finished. Now notice the reason that you're finished is that both of these hypotheses have been discharged. They're no longer in the proof. If one of these hypotheses had not been discharged and you had somehow derived R, you would not be done. You'd have an undischarged hypothesis, and the proof would not be correct. Okay? So that's how that works when we're trying to use conditional introduction in conjunction with or elimination, and you'll get lots of practice doing that. Okay, finally, we have the idea of nested conditional introductions. Now, what we mean by nested is essentially that one is occurring within or inside another. So let's show how that works. So sometimes we need to prove a conclusion whose main operator is a conditional, but whose consequent is also a conditional. So for example, we could be asked to prove if Q then, if P then R or L, or we could even be asked to prove if Q then, if P then, if R then L. Now in a case like this, either of these cases, what we would do is proceed, typically we would proceed by conditional introduction by hypothesizing Q. We'd hypothesize Q. And in the first case, what we would do is say that, oh, well, now we have to now we have to derive if P then R or L. But since my task is to derive if P then R then or L, I could once again hypothesize P and just derive R or L. Okay? So in the first case, we might hypothesize Q in order to derive if P then R or L, but then we might also immediately hypothesize P in order to derive R or L. Now in the second case, the same reasoning would apply, but we'd actually make three distinct hypotheses. First, we'd hypothesize Q, then we'd hypothesize P for the purpose of deriving if R then L, but seeing that even this is a conditional, we would hypothesize R and then just focus on getting L. So let's see how that works in an actual proof. So here we're asked to prove a conditional so the main operator is a conditional, but the consequent is also a conditional. So that suggests the following strategy. We only got one assumption, P and Q then R, and we hypothesize Q. When we hypothesize Q, our aim is to derive if P then R or L. But then noticing that that's our aim, to derive if P then R or L, we go ahead and hypothesize P. Now notice that this requires us to indent still again, right? So we indented one time, then we indent another time for the second hypothesis. If there were a third hypothesis, we'd indent still again. And that's the nesting aspect of this. Okay, so we hypothesize P. Now, importantly, as soon as we hypothesize P, our task shifts yet again to just deriving R or L. So now we are totally focused on deriving R or L. Now, if you look at this, you can see that this is quite easy to do because we have P right here and we have Q right here, which gives us P and Q, which will therefore give us R by conditional elimination, and R or L by disjunction introduction. So that's what we do. P and Q, R or L. And now we say, okay, I have just shown if P then R or L. So I have actually demonstrated this conditional, if P then R or L. So I assert it, if P then R or L, taking away the second indent and dropping a line, which of course means that all of this now has been discharged and is no longer available for use. But of course, I don't want just if P then R or L. I want if Q then if P then R or L. Well, what's cool is that we actually have it. We hypothesized Q and we derived if P then R or L. So on line 8, we can assert if Q then if P then R or L now by two through 7, right? Q, P, then R or L. So if Q, then if P, then R or L. And we drop a line discharging the first hypothesis. And so now we've actually demonstrated the conclusion, if Q, then if P, then R or L. And if you look at the proof, you'll see that this hypothesis is nested or contained in the first hypothesis. Okay, so just to emphasize a few features of this, note that each time you create a hypothesis, your immediate goal changes. So initially, you're trying to demonstrate this whole conclusion, but then you hypothesize Q, and now your focus became if P, then R or L. But after you decide to go ahead and hypothesize P, your goal then became to derive R or L. So initially your goal was to derive the entire conclusion. After hypothesizing Q, your goal became to derive if P, then R or L. After hypothesizing P, your goal became to derive R or L. So you have to change your mindset each time you take on a new hypothesis. Remind yourself what it is that you're trying to prove. Okay, so now we'll go ahead and just do some review questions. I'm going to, these questions are going to lead you through a proof that I wouldn't necessarily expect you to be able to do right now because it's a little bit more complicated than the ones that we just did. But I do need you to be able to understand each step. And at the end of this, you should be able to sit down and replicate this proof. A really good test of your comprehension of this rather long video is whether or not you could replicate the proof that you're going to sort of troubleshoot right now. Okay, so as usual, go ahead and pause each time I bring up a new slide because the answer will be coming very shortly. I should have said that your goal here is just to, in each case, say whether or not the move that's highlighted is a correct move. And if it's not, then try to tell yourself why.